Students, coming to the discussion of Threo and erythro isomers. The Threo and erythro isomers arises only when the molecule contains more than one chiral carbon. When a molecule contains more than one chiral carbon atom and more than one structures and more than one isomers are possible for a given one. And if you consider the molecule which is on the board, remember, on the chiral carbon atom, if the identical groups are present towards the same side of the chiral carbon atom, then it is called as erythro isomer. If the similar groups are present in the opposite direction, then it is called as Threo isomer. I mean to say, if the similar groups are present on the same side of the chiral carbon atom, then it is called erythro. If the identical groups are present in the opposite direction on a chiral carbon atom, then it is called as Threo isomer. Then the most important discussion is optical activity in biphenyls. Biphenyl is a molecule in which the two benzene rings are linked to one another through a single bond. As the two benzene rings are linked to one another through a single bond, free rotation is possible around carbon-carbon single bond. When both the rings are present in the same plane, then the biphenyl is said to be coplanar. And remember, for any molecule to be optically active, we have already learned the molecule must not have a plane of symmetry. If two benzene rings are linked to one another through a single bond, and when both the benzene rings are present or lies in the same plane, then the molecule is having plane of symmetry. In such case, it becomes optically inactive. When ortho and ortho dash positions of a biphenyl molecule substituted by a bulky groups, the hydrogen atoms present at ortho and ortho dash position of one benzene ring and ortho and ortho dash position of another benzene ring are substituted by bulky groups such as N-moto, CH3, SO3H, COOH, etc. Remember, let us consider A and B are the two different bulky groups which are present at ortho dash position of one benzene ring, and C and D are the two benzene rings which are present at ortho and ortho dash positions of another benzene ring. When such the hydrogen atoms at ortho and ortho dash positions of a biphenyl molecule are substituted by bulky groups, in order to minimize the steric hindrance, one of the benzene ring rotates through, remember, one of the benzene ring rotates through 90 degree. When one of the benzene ring rotates through 90 degree, then the molecule becomes non-planar. So, when the molecule becomes non-planar and the groups which are present at ortho and ortho dash positions, when they are not identical, I mean to say A should not be equal to B and C should not be equal to D. A and B should be different. I mean the two different groups present at ortho and ortho dash positions of one benzene ring should be different. A should not be equal to B and C should not be equal to D. C should not be equal to B. In such case, the molecule loses plane of symmetry. I mean to say, when A is not equal to B and B, C is not equal to C is not equal to D, the first point to minimize the steric hindrance, one of the benzene ring rotates to 90 degree and the molecule becomes non-planar. And when the A is not equal to B and C is not equal to D, it is not possible to divide the molecule with any plane to get a two identical arc. As a result, the molecule loses the plane of symmetry. When once the molecule is not having a plane of symmetry, it becomes optically inactive. So, any biphenyl molecule becomes optically active under the following conditions. I mean to say, the two benzene rings must be non-planar, and you can make the molecule non-planar by substituting the ortho and ortho dash hydrogens of both the benzene ring by bulky groups. When once the ortho and ortho dash hydrogens are substituted by bulky groups, to minimize the steric hindrance, one of the benzene ring rotates through 90 degree and the molecule becomes non-planar, and the atoms, when the groups which are present at ortho and ortho dash positions are different, then the molecule loses the plane of symmetry. Then Absence of plane of symmetry is sufficient enough for a molecule to become optically active and to rotate the plane polarized lines. Okay, so this is a brief about our optical activity in biphenyls. Okay.